Welcome to White Space. What actually were the cosmic dark ages? Put this on in the background, close your eyes if you want, and let the story carry you. Let's begin. Pick any direction. North, south, straight up through the ceiling. Now push your imagination outward, past the orbit of the Moon, past Mars and Jupiter, out beyond the edge of our solar system into the vast interstellar space between stars. Keep going, past the Orion arm of the Milky Way, past the center of our galaxy, past the Magellanic Clouds, past the local group and onward, deep into the filaments and walls of the cosmic web. At some point on that journey, you would pass through a region of space so empty, so geometrically desolate that your mind would struggle to process what it wasn't seeing. No galaxies, no galaxy clusters, no nebulae glowing with star formation, just an almost perfect sphere of nothingness, 330 million light years from wall to wall. This is the KBC void. It is one of the largest known underdensities in the observable universe, a region where matter appears to have simply refused to gather. If our solar system had formed somewhere near the heart of this void, humanity might have spent its entire history staring at a night sky that contained almost nothing. No Andromeda, no Triangulum, not even a hint that galaxies beyond our own existed at all. The cosmos would have seemed a far lonelier place. And yet even this, one of the emptiest addresses in the known universe, is far from the deepest darkness the cosmos has held. To find true void, we have to go further. Not across space, but back through time. Back before the first galaxy, back before the first star. Back to an era that astronomers call the cosmic dark ages, a stretch of hundreds of millions of years when the universe contained all the raw materials needed for stars to exist and yet produced none. That is the place we are trying to reach. That is the silence we are trying to hear. In 1990, when astronomers pointed Hubble at the sky for the first time, they expected a revolution. What they got first was humiliation. The mirror, polished to a precision better than 1 part in a million, had been ground to the wrong shape. The error was less than a quarter of the width of a human hair, but at the scale of optics it was catastrophic. Images came back blurred, soft, useless for the deep field work that justified the telescope's enormous cost. Congress was unhappy. The press was scathing. The telescope became a symbol of institutional failure. The repair mission in 1993 restored its sight, and in the years that followed, the pressure to justify the investment drove astronomers to ask increasingly audacious questions. What is the furthest thing we can see? What does the universe look like at its youngest? How far back can we reach? The answer began not with a bold announcement, but with a long, quiet stare. Astronomers chose a region of sky so barren of visible objects that pointing a telescope there seemed almost wasteful, a patch smaller than a grain of rice held at arm's length. They let the light accumulate for days, and when they finally looked at what had gathered on the sensor, they found it was not empty at all. It was thick with galaxies, thousands of them, spirals and ellipticals and irregular smudges. Some nearby, some extraordinarily distant. The image became known as the Hubble Deep Field, and it told astronomers something they had suspected but never confirmed with such clarity. Wherever you look, in any direction, the universe is full. But that image also contained information of a more subtle kind. The galaxies in it were not all the same age. The closer ones appeared sharp, blue-white, with the light of active star formation, similar to our own Milky Way today. The more distant ones were fainter, redder, less structured, not because they were small or dim, but because the light from them had been traveling for so long that the expansion of the universe had stretched it, pulling its wavelength from the blue end of the spectrum toward the red. This stretching is not metaphorical. It is a direct consequence of the expansion of space itself. A photon emitted by a galaxy 10 billion years ago in the ultraviolet has, by the time it arrives at our detectors, been stretched all the way into the infrared. The more distant the source, the greater the expansion it has traveled through and the more extreme the shift. Astronomers call this redshift. It is simultaneously a measure of distance and of time. And by reading redshift, we can sort the galaxies in the deep field by age, peeling back layers of cosmic history like strata in rock, each layer representing an earlier chapter of the universe's life. The oldest galaxies we see in deep field images formed only a few 100 million years after the Big Bang. Small, irregular, intensely bright, almost nothing like the elegant spirals we see nearby. The universe was still learning how to make galaxies. But even these oldest visible galaxies are not the beginning. They tell us we are close to the frontier, but they also tell us the frontier is real. Push back another few 100 million years and the deep field goes dark. Not because there is nothing there, but because there is nothing that emits light in any wavelength that optical or infrared telescopes can reach. We have arrived at the edge of the observable universe and found a wall of silence. Beyond that wall is what we are looking for. To understand what the cosmic dark ages actually were, we need to go back much further, to the very first moments after the Big Bang. In those earliest fractions of a second, the universe was not dark. It was the opposite, an almost incomprehensibly dense plasma of radiation and matter so thoroughly intertwined that light could not travel even a centimeter before being absorbed and re-emitted. There was no such thing as a photon that moved freely from point to point. Energy existed in enormous quantities, but it was locked, trapped in a perpetual cycle of emission and absorption, unable to go anywhere or illuminate anything in any meaningful sense. As the universe expanded, it cooled, and cooling changed the relationship between radiation and matter. For the first 380,000 years of cosmic history, the universe was dominated by radiation. Its energy density exceeded that of matter. And this imbalance kept everything ionized. Electrons and protons existed as separate particles, never settling into the stable atoms they were trying to form. Every time a proton captured an electron, a nearby photon blasted it free again. The universe was in a state of perpetual frustrated chemistry. Then, at around 380,000 years after the Big Bang, the temperature dropped below 3000 Kelvin. At that threshold, which sounds hot by human standards, but was, by the standards of the early universe, nearly cold, the energy of photons was no longer sufficient to ionize freshly formed hydrogen atoms. For the first time, electrons and protons could combine and stay combined. Hydrogen atoms formed in their billions, then their trillions, then across the entire observable volume of the cosmos simultaneously. And as they formed, the photons that had been endlessly bouncing between charged particles suddenly found the universe had become transparent. For the first time, light could travel freely across cosmic distances. We can still detect those photons today. They are the cosmic microwave background, a faint hiss of radio waves arriving equally from every direction. The oldest light in the universe, a photograph of the cosmos taken at the moment it first became transparent. When we look at maps of the CMB, we are looking at the universe as it existed 380,000 years after the Big Bang. It is the most ancient image we possess. But here is the thing, that image shows no stars, no galaxies, no large-scale structure, just a nearly uniform field of photons, with tiny fluctuations in temperature, fluctuations of less than 1 part in 100,000 that hint at very slightly denser and less dense regions of gas. After the CMB was released, the photons scattered outward and the universe entered a new phase. The light faded, the temperature dropped. The glow of the Big Bang cooled through orange, through red into the deep infrared, and then below any threshold our eyes could register. The universe went dark. For the next 200 million years, it stayed that way. To the casual observer imagining a hypothetical presence inside this early universe, there would have been almost nothing to see, no stars, no glowing nebulae, no distant galaxies scattered across the sky. Just an extraordinarily diffuse haze of hydrogen and helium gas, cooling slowly as it expanded, drifting through a darkness that had no edges. But beneath that apparent emptiness, something was already at work. Something invisible, massive, and inert, at least to any form of electromagnetic radiation. Something that would, over the hundreds of millions of years of the Dark Ages, build the scaffolding on which every galaxy, every star, and every planet in the observable universe would eventually be constructed. Dark matter, the existence of dark matter, was first inferred not from theory but from observation, and the observation was simple enough to state the stars in spiral galaxies were moving too fast. The outer stars in a rotating galaxy should, by the same logic as planets in a solar system, move more slowly the further they are from the gravitational center. Mercury moves faster than Neptune. Inner galactic orbits should move faster than outer ones. But when astronomers in the 1970s measured the actual rotation curves of dozens of galaxies, they found the opposite. Outer stars maintained roughly constant velocities regardless of the distance from the center. There was only one consistent explanation. The visible matter, the stars and gas that emitted light, was not all the matter that was there. Something else, something that emitted no radiation and interacted with nothing electromagnetically, was distributed through and around the galaxy, adding mass to regions that optically appeared empty. The more mass there is, the faster the orbits can be, and the flatter the rotation curve. Whatever this unseen substance was, it accounted for roughly 5 times as much mass as all the visible matter in the universe combined. We could not see it, touch it, or detect it directly. We could only infer it from the way it bent and accelerated everything around it through gravity. Dark matter changed the narrative of the cosmic dark ages entirely. Because while the gas in the young universe was cooling and doing very little of structural interest, the dark matter was not standing still, it was collapsing. Unlike hydrogen and helium, which could radiate away energy when compressed and eventually form stars, dark matter had no mechanism for energy loss. It could not emit photons, it could not shed heat. This meant that as it fell under gravity into denser regions, it could not collapse into a compact body the way normal matter could. Instead, it stretched into the shapes that gravity and angular momentum allowed. Sheets, filaments, and at their densest intersections, extended halos. The result over hundreds of millions of years was the cosmic web, a 3-dimensional network of dark matter structure that spanned the entire observable universe. From the outside, if you could somehow see it, it would look biological, like a neural network or the interior of a sea sponge or a vast network of soap bubbles pressed together. Dense nodes at the intersections, thin filaments connecting them, and enormous voids between. All of this happened in darkness, unannounced and unobserved. The ordinary matter, the gas, followed. It was pulled gravitationally into the same filaments and halos where the dark matter had concentrated. It began to stream along those invisible highways, pulling at the intersections, building up in the halos that the dark matter had already assembled. The universe was preparing. The scaffolding was going up. But the building had not yet begun. Here is the question that would consume astronomers for decades. How do we know any of this? How can we observe an era when there was no visible light? How can we read the architecture of a structure that emits nothing we can detect? The answer was discovered not by someone searching for the cosmic dark ages, but by a Dutch astronomer in wartime hiding, looking for a way to map his own galaxy. Jan Oort had spent years building a career on a single profound act of humility, accepting that the Sun was not at the center of the Milky Way. By carefully studying the motions of distant stars, he had shown that the galaxy was far larger than anyone had imagined, and that our solar system sat well out toward the periphery. But mapping the galaxy's full structure required seeing through the dense dust clouds that obscured large sections of it from optical telescopes. Radio waves passed through dust. If there were something in space that emitted radio waves at a specific identifiable frequency, astronomers could use it as a tracer, a way of seeing the galaxy's hidden structure. Oort thought hydrogen might be the answer. Hydrogen was the most abundant element in the universe. If it emitted radio waves at a characteristic wavelength, those waves would penetrate the dust and reveal the gas clouds that optical telescopes could never see. He assigned the problem to his student, Hendrik van der Hulst. The question was whether neutral hydrogen emitted any radio signal at all, and if so, at what frequency. Van der Hulst went through the physics carefully. The hydrogen atom, a single proton orbited by a single electron, could emit photons when its electron changed energy states. Most of these transitions produced photons in the ultraviolet or visible range. But there was one transition that was different. Inside the ground state of hydrogen, there was a tiny energy split between two configurations, one where the electron and proton spun in the same direction, and one where they spun in opposite directions. When an electron spontaneously flipped its spin from the parallel to the antiparallel configuration, it released a photon of a very specific energy, corresponding to a frequency of 120 MHz or a wavelength of 21 centimeters. This was a radio wave. The transition was extraordinarily rare. Any individual hydrogen atom might sit in the higher energy state for 11 million years before spontaneously flipping. But space contains an enormous number of hydrogen atoms, and 11 million years is a short time by cosmic standards. Across the galaxy, the 21 centimeter line would be emitted constantly from everywhere that hydrogen existed. By the early 1950s, Van der Hulst's prediction had been confirmed by independent groups in the United States and the Netherlands. The signal was real. Hydrogen, invisible to optical telescopes, was broadcasting its presence across the radio spectrum, everywhere in the galaxy simultaneously. The implications for cosmology would take decades to fully appreciate, but they were staggering. Because if hydrogen emits at 21 centimeters and the universe expands, then hydrogen emitted in the early universe would reach us redshifted. Hydrogen from deep in the dark ages, when the universe was a fraction of its current size, would arrive at us stretched to wavelengths of 2 meters or more. In principle, if we built a radio telescope sensitive enough, we could detect the hydrogen gas from the era before any stars existed. We could listen to the Dark Ages directly. The physics of what such a signal would tell us is subtle but powerful. During the cosmic Dark Ages, hydrogen gas existed in two states. Some of it was in the clouds that followed the dark matter filaments, slowly cooling and collapsing. Some of it remained diffuse, filling the spaces between those clouds. The 21 centimeter emission from this gas would have had a very specific intensity determined by the temperature of the gas relative to the background radiation field. When the temperature of the hydrogen was lower than the background radiation temperature, the gas would absorb 21 centimeter photons rather than emit them, appearing as a shadow against the backdrop of the CMB. When the gas was hotter, it would emit, appearing as a glow. The pattern of absorption and emission would encode in extraordinary detail the density and temperature structure of the early universe. And then the first stars would change everything. By around 200 million years after the Big Bang, the gas in the densest nodes of the dark matter web had been compressed past a critical threshold. The pressure and temperature at the center of these collapsing clouds became sufficient to trigger nuclear fusion, the process of fusing hydrogen nuclei together to form helium, releasing enormous quantities of energy in the process. The first star ignited, and then another and another, scattered across the universe at the densest intersections of the dark matter filaments. The lights came on one by one, not with any coordination, not simultaneously, but across hundreds of millions of years of cosmic history. In every direction, the first stars began to burn. These first stars were unlike anything in the present-day universe. They formed from pristine hydrogen and helium, without the heavier elements that later stars would contain. This made them extremely massive. Some may have been hundreds of times the mass of our Sun, and intensely hot. Their surfaces blazed at temperatures of 100,000 Kelvin or more, flooding their surroundings with ultraviolet and X-ray radiation. That radiation had a decisive effect on the surrounding gas. Ultraviolet photons above a certain energy threshold, 13.6 electron volts, the ionization energy of hydrogen, could strip the electrons from neutral hydrogen atoms, converting them back into the free protons and electrons they had been in the pre-recombination era. The first stars were literally reionizing the universe, reversing the process that had ended the radiation-dominated epoch hundreds of millions of years earlier. At first, each star produced only a small bubble of ionized hydrogen around itself, a sphere where radiation had cleared the neutral gas away. But as more stars formed, and as those stars evolved and exploded as supernovae, seeding the surrounding gas with heavy elements and triggering further star formation, the bubbles grew. They merged. They spread across cosmic distances. This epoch, the era of reionization, lasted from roughly the first stars at 200 million years to a fully ionized universe at around 1 billion years after the Big Bang. It is the transition from the cosmic dark ages to the recognizable universe we see around us today, and it is almost completely unobserved. We have snapshots of the universe before reionization in the form of the CMB. We have snapshots of the universe after it in the form of the quasars and galaxies visible at redshifts below 6. But the transition itself, the lighting of the universe, is still largely a blank page. The 21 centimeter signal is the key to filling that page. As the bubbles of ionized hydrogen grow during reionization, they carve out regions where the 21 centimeter signal goes silent. The neutral hydrogen inside the bubble has been ionized. It no longer emits or absorbs at that wavelength. The result in the radio sky is a pattern of structures, bright regions of neutral hydrogen alternating with dark holes where ionization has swept through. The shape of those holes encodes information about the sources creating them, their intensity, their spectrum, their number density, how quickly they formed. By mapping this pattern across different redshifts, which corresponds to different times in cosmic history, we can watch the reionization process unfold in real time. We can identify when and where the first stars and first galaxies formed. We can test our models of the dark matter web and of how normal matter flowed into it. We can, in principle, reconstruct the entire sequence of events from the first seconds after the CMB was released to the moment the universe became transparent for the second time. In 2018, a small experiment stationed in the Australian desert announced what appeared to be a detection. The Aegis instrument, a pair of flat metal panels lying on the ground like metallic wings spread wide, had been scanning the sky for the redshifted 21 centimeter signal from the era of the first stars for over a decade. The team found an absorption feature in the radio spectrum centered at a wavelength consistent with hydrogen emissions from roughly 180 million years after the Big Bang. This alone would have been the most significant measurement in cosmology in years. But the feature was deeper than any theoretical model had predicted. The gas appeared far colder than it should have been cold enough that conventional physics had no explanation. One proposal stood out for its audacity. Perhaps dark matter was not as inert as assumed. In the cooler, denser environment of the early universe, before reionization had heated everything, perhaps dark matter could interact directly with normal matter through some as yet unknown force, scattering off hydrogen atoms and carrying heat away from the gas. This would explain the unexpected coldness, but at the cost of revising our entire picture of what dark matter is. The astronomical community responded with the appropriate mixture of excitement and skepticism. The EDGE's result was extraordinary, and extraordinary results require extraordinary scrutiny. Independent experiments set to work attempting to reproduce it. An antenna floating on a lake in southern India, part of an experiment called SARAS, concluded that its own measurements were inconsistent with the extreme absorption depth that EDGE's had reported. The most dramatic interpretation, dark matter cooling the primordial gas, faded from the front pages. The simpler explanation, a systematic error in the EDGE's analysis, became the working hypothesis. But the birth certificate remained. Even if the precise depth of the signal was contaminated, the timing, the first stars forming around 180 million years after the Big Bang, is consistent with other lines of evidence. The search, even when it produces contested results, is teaching us things. Every failed or ambiguous detection reveals something about the difficulty of the measurement, the nature of the foreground signals, the improvements needed in the next generation of instruments. The next generation is already under construction. Across the same remote desert in Western Australia, engineers and astronomers are assembling what will eventually be the most powerful radio observatory in history. The square-kilometer array will consist of tens of thousands of individual antennas spread across hundreds of kilometers, linked together by high-speed computing infrastructure that will process data volumes larger than the entire global internet traffic of today. Its sensitivity to faint radio signals will exceed anything previously built by orders of magnitude. It will still not be enough to fully characterize the Dark Ages. The problem is not the telescope itself, but the environment. Earth's atmosphere, saturated with radio emissions from human technology, mobile phones, aviation radar, satellite communication, creates a noise floor that even the most sophisticated filtering cannot fully remove. The very civilization that built the technology to ask the question is also generating the interference that prevents us from hearing the answer. The logical solution is to leave the atmosphere behind. The far side of the moon is the quietest place in the inner solar system. It is permanently shielded from Earth's radio emissions by the body of the moon itself. And the absence of any lunar atmosphere means there is no ionospheric distortion of incoming signals. A radio telescope on the lunar far side would have access to frequencies and sensitivities that are simply inaccessible from the ground. Several missions are now in planning stages to test antenna deployments there. The universe cooperated in another way too. The CMB itself, which has been mapped in extraordinary detail by missions like Planck and WMAP, contains in its temperature fluctuations the seeds of everything that would follow. The slightly denser regions in those maps, regions of 1 part in 100,000 above the average density, are the sites where the dark matter web would eventually thicken, where gas would pool, and where the first stars would eventually ignite. The history of the cosmic dark ages was written in faint pencil. At the very moment the universe became transparent for the first time, we are now learning to read that writing. There is a deeper question buried in all of this, one that goes beyond the technical challenge of building the right antenna or finding the right radio frequency. It is a question about what we mean by light and darkness themselves. The human visual system responds to a narrow slice of the electromagnetic spectrum, a window defined by the physics of our atmosphere and the biochemistry of our retinas, spanning wavelengths from roughly 400 to 700 nanometers. That window is extraordinarily useful for navigating the world at human scales. It is almost entirely useless for cosmology at the deepest scales. The universe communicates across the full electromagnetic spectrum. It broadcasts in gamma rays and X-rays from the violent accretion of matter around black holes. It glows in the infrared from the dust clouds where stars are forming. It speaks in radio waves from pulsars, from the CMB, from the 21-centimeter line of hydrogen, and from the red-shifted echoes of the first gas clouds that formed along the dark matter filaments 200 million years after the Big Bang. Every time astronomers have built a new kind of eye, tuned to a wavelength that no human retina can access, the universe has appeared suddenly more populated, more structured, more active than it had seemed before. X-ray telescopes revealed a universe boiling with energetic processes invisible in optical light. Radio telescopes revealed the structure of our own galaxy and of distant quasars and jets. Infrared telescopes revealed the birth of stars hidden inside their own dust. Each new window did not just add to the picture, it transformed it. The cosmic dark ages were never truly dark. They were dark to us, dark to the narrow window of wavelengths our eyes were built for, to a hypothetical being tuned to radio frequencies. The universe at 200 million years old would have blazed with the 21-centimeter emission of 1 billion cubic light years of hydrogen gas, mapped in exquisite detail against the filaments and voids of the dark matter web. Structure would have been everywhere in the patterns of density and temperature imprinted across the radio sky. What we call darkness is really just a description of our own instruments. Think about what it means to have evidence of the first stars. Every heavy element in your body, the iron in your blood, the calcium in your bones, the oxygen in every breath, was forged inside a star. Hydrogen fusion builds helium. More complex fusion in more massive stars builds carbon, oxygen, nitrogen. Supernova explosions produce elements heavier than iron, scattering them across surrounding gas clouds that will later collapse into new stars and new planetary systems. You are, in a literal and non-metaphorical sense, a collection of stellar remnants. The atoms that compose you were once inside a star. Some of them may have been inside many stars. The first stars were the beginning of that chain. They were the first objects in the universe capable of producing anything other than hydrogen and helium. They may have been short-lived. Massive stars burn fast and die violently, but they seeded the surrounding gas with the first heavy elements, changing the chemistry and cooling properties of the clouds that followed, making the next generation of stars cooler, longer-lived and more varied. The universe we live in, rich chemical diversity, its rocky planets, its carbon-based life, could not have existed without those first stellar objects. They are not a curiosity in the history of cosmology. They are the origin point of everything complex. And we do not know when they formed exactly. We do not know how massive they were. We do not know how many formed in a given volume of space, or how quickly they transformed the chemistry and temperature of their surroundings. We do not know the time scale over which their ultraviolet radiation began dissolving the neutral gas that surrounded them, or at what point the first isolated ionized bubbles merged into the cosmic foam of reionization. We know the universe was dark, and then it was not. What happened in between is still mostly a story we have inferred from fragments, a narrative constructed from boundary conditions, the CMB on one side, the observed quasars on the other, with almost nothing from the critical middle chapter. That is the chapter we are trying to recover. The history of astronomy is largely a history of learning to look in new ways. Galileo did not invent magnification, he pointed it at the sky. Herschel did not invent infrared. He measured it in an experiment about sunlight and realized, in a moment of accidental discovery, that heat extended beyond the red end of the visible spectrum. Jansky did not set out to discover cosmic radio emission. He was mapping radio interference for Bell telephone and found a hiss that rotated with the stars. The discovery of the cosmic dark ages will follow the same pattern. The tools being built now, the vast radio arrays, the algorithms to strip galactic foregrounds, the eventual lunar antennas, are being aimed at a signal so faint that it exists at roughly 1,000th the intensity of the radio emission from our own galaxy, sitting at precisely the same frequencies. Finding it is not like looking for a needle in a haystack. It is more like listening for a specific whisper in a thunderstorm, while someone holds a loudspeaker next to your ear. But the signal is there, we know it is there, the physics demands it. The history of hydrogen from the recombination era through the dark ages through reionization is encoded in the radio sky. We simply have not yet built instruments sensitive enough, or quiet enough, or precise enough to read it cleanly. When we do, the picture of the early universe will change in ways we cannot fully predict. The timing of the first stars will be pinned down, the mass spectrum of population 3 objects, the ancient metal-free stellar behemoths of the first cosmic era will be constrained. The question of whether dark matter is truly inert or whether it can interact with ordinary matter in the cold conditions of the pre-stellar universe will be tested with data rather than speculation. The topology of reionization, whether it proceeded rapidly or gradually from the densest regions outward or from the diffuse gas inward, will be mapped across billions of light-years of cosmic volume. We will, for the first time, have a direct observational window into the era that made the universe what it is. 200 million years is a number almost impossible to hold in mind. The dinosaurs went extinct 66 million years ago. The continents looked broadly familiar 300 million years ago. 200 million years takes us back to a world with no flowering plants, no mammals, no birds, just reptiles and ferns and shallow seas. And yet the cosmic dark ages lasted 3 times that long, unfolding in complete optical silence, building the invisible foundations of everything that followed. In that long dark interval, the universe was not waiting, it was working. Dark matter was condensing into halos and filaments. Gas was streaming along those filaments under gravity. The first molecular hydrogen was cooling cloud cores below the threshold for fragmentation. The first protostellar objects were gathering mass from their surroundings, heating their interiors, pressing toward the conditions for fusion, and at some moment, some specific moment in cosmic time, in some specific cloud, in some specific node of the dark matter web, a pressure wave crossed a threshold, and hydrogen fusion began. A star ignited. For the first time in the history of the universe, an object existed that was not merely responding to gravity, but actively generating energy by rearranging matter at the nuclear scale. That first star did not know it was the first. It burned for a few million years, as massive stars do, fusing hydrogen to helium, helium to carbon, carbon to oxygen, until the fuel ran out, and it collapsed under its own weight, and either imploded silently into a black hole or erupted as a supernova, scattering its heavy elements across the surrounding gas. It left no record of itself that any telescope has yet detected. Its light has been redshifted beyond our current reach, but it was there. We can infer it from the chemistry of the oldest observed stars, which contain trace amounts of the heavy elements that only a prior generation of stars could have produced. We can infer it from the ionization state of quasar absorption spectra, which show the reionization was well underway by redshift 6, meaning the process had begun much earlier. We can infer it from the physics of structure formation, which requires that the first dense enough objects appeared within the first few 100 million years. The first star is the invisible hinge on which all of subsequent cosmic history turns. We are living in a universe that has spent 13.8 billion years building itself out of darkness. The galaxies, the stars, the planets, the carbon and oxygen and nitrogen that make up living things, all of it emerged from a starting point of near-perfect uniformity, guided by the hidden architecture of dark matter, sparked into brightness by a generation of massive, short-lived stars that have left no surviving descendants. The darkness at the beginning of time was not a failure of the cosmos to produce structure. It was the structure forming silently in wavelengths our eyes do not reach, in time scales our lives cannot encompass, in places our instruments have not yet found quiet enough to hear. We are still building those instruments, we are still writing those algorithms, we are still learning to listen to the universe in the frequencies it prefers. But the signal is there, and every year the noise floor drops a little. Every year the threshold of our sensitivity advances toward the whisper that has been waiting for us since the universe was, by our reckoning, dark. We were never looking in the right direction. We were never using the right eyes now. Slowly we are learning what the universe has been trying to tell us all along, not from the stars that filled the cosmos with light, but from the darkness that came before them and made them possible.